Okay. So, thank you for having accepted so illicitly my talk. Yeah, I come from Aachen, as said, and we operate with students ground station. This is my team. Basically, the idea was because we realized that it's not only suffice to want to build a satellite, you also need to operate a satellite. And obviously, if you have no practice in this field, it's you're going to have a really hard time operating a satellite. Okay, so since I am the last talk, it will not be too much technical, and I try to make it really fast and show more practical aspects and a lot of photos. So I will present our ground station, then I present how we operate it and what from our point of view is worked very well and what was important to us. And then I show some selected operations we did on CubeSats, and then also on two PocketQube, one that really is still in my heart, and one other, the $50 set, which was a really nice satellite. Okay, so this is our team. So the purpose of operating our ground station was not just to focus now on one satellite, but to bring space to the students, which normally are more like theoretical, and this now it's a little bit more practical stuff, and it's mostly also for diverting, you know. So that's why you could operate a ground station just by one or two person, but we try to break it down in different sections so that many students can focus on the thing they like. That's why we test also a lot of radios from the Simple Fun Cube, which was actually our very first receiver. HackerRef, okay, we're not so happy with HackerRef, but it works. Mostly we use this RTL dongle, which is very nice, considering the price. We have also more serious stuff like Rode and Schwarz. For S-band, oh, now it's D-band. We have ICOM, of course, and several rotors. We have several antennas. When you operate what's my student like the word multi-mission ground station, you need, of course, a lot of antennas. So that's why we have antennas for the S-band. We have antennas, we have the Yagi arrays, we have a Lindenblatt, quadrifilar antennas. We also make some experiments, nice experiment here, with a telescope mount as the rotor. It's not too optimal because actually this mount produces a lot of noise, so yeah, you have to know when you start listening or when you start transceiving. Okay, so that's the flow sheet. I promise not too technically, just to know every color is a different teleport. So basically we have 3 teleports and one in construction. The new one in construction is because actually we wanted to adhere to ZNOx. Then we went to our professors and they said, oh no, you have to operate and all the ground station has to be run. Who will pay this and what's about the security? So we decided to make a new a teleport which is outside of the university in somebody's home, not somebody's home, but we will operate it with the local, at the local Sternwarte. Yeah, and so we will not have any problem with the IT and people that think that it might be a problem. So this is our backend. So this is here our main control room. Basically, as we are a quasi no budget club, if you want. So we use every monitor and every computer that we possibly can have from people that don't need it anymore. This is our briefing room because yeah, operating also if we just track some satellites, we brief our team. We have schedules. We have people that really knows. Okay, this is my shift, day shift. We have night shift, which is when you operate this in a university quite challenging, because university have open and close times. So you have to manage also this and be nice to everyone and hope that they close both eyes and don't look too much. Okay, so what we use is, this looks quite old and complicating, but again, the purpose is to make the students work in the field and not just press a button and wait that the data comes from anywhere. So that's why we use different tracking systems. Here is our most favorite is Orbitron, because yeah, it has this nice DDE driver that we back engineered in order to be able to send tracking information to the rotors or to the receivers, and from then we wrote an own little software that is able then to connect Orbitron to whatever. At the heart, we have a virtual machine, and in this virtual machine we are running Hamlib, which is pretty cool because this is kind of an abstraction layer, and so we can just by downloading drivers or by fixing existing beta drivers or writing completely new drivers, connect to very old hardware. This is really a little diva, this rotor controller, or to more advanced rotor controller like this SBIT. So there's for everyone a lot of work, and yeah, we are happy. We are happy to have the students that are really enthusiastic. We have students that don't want to program but operate, and we have students that are more, yeah, like the hacker guy, you know. Okay, and then for decoding, of course, if you say if you want to decode, let's say the ideal case, every satellite, you need a lot of knowledge about how to decode this particular satellite, because every team has its new standard or its way how to decode, and of course this is also part of the science. That's why we send PocketQubes or satellites in space, because we want to test our science or our new constructions. So, and that is something you have to be aware of, and yeah, follow the actual technology. Yeah, so if you want to mission operation needs, how did we get started? So basically, you need people that want to actually fly the satellite. Most people want to construct the satellite, but we want to fly the satellite. My students are people that dream one day maybe getting into ESOC or controlling satellites, or so this is the people you need. When the student comes first, he will be trained, and then he has to perform a operation driving license. And here you see some of the students that performed this driving license. This is the professor, the project manager of Star Seas, which allowed us to perform real mission operation and uplinking commands. And when he visited us, he also had to do the driving license. Because we perform a mission operation also for foreigners, you have a problem, you can ask us, and we help you on a best effort basis. That's why, and also because you operate 3 different teleports. We installed a communication loop. This is communication loop of ESA. It's not that advanced, but we use freeware software, and it's working quite well. So you can sit in Japan, for example, and perform the mission operation with us in direct, also with communication, and also log on to our consoles and also operate our consoles if you want. And because we are many people and because everything is moving all the time, we also implemented procedures. Procedures are nice because once they are well written, you can install here. You see these two guys. At that moment, they were already sitting like 6 hours, so they did it the night. And at ease with their coffee mugs. So it's really important to implement good documentation, break broken everything down in procedures, and and train, practice. Also, maintenance is one thing. With your new development, maybe this will be something that we don't need anymore. But at the moment, we have also a maintenance team, and this is very important. Okay, so now you have your ground station, and now you need to get familiar with the ground station. And there are a couple of interesting spacecrafts actually, very easy ones and also very advanced ones. So we chose first to start with weather satellites. Why weather satellites? Because first they're really easy. You don't need big technical background. You have your radio station. You plug it into this nice decoder that is provided. And when everything works, so this is a signal. And even then, it's challenging because you have to think about problems like sampling rates, the right recorder bandwidth. You have to track the Doppler. But at the end, if you are successful, and normally this is something that after one day or 2 days, you get a nice picture, and for us, this is really like cool. Huh? Okay, another interesting point with the web SDR of Norway, you can also capture weather satellites because they have really strong signal, and you can then also shift the Doppler with your hand. It's possible. It's quite challenging, but if you get the right image, then you are ready to go and to operate it then on the ground station. So first, our students make it on the web SDR. This is like the exam, and then we teach them to operate it with the real ground station. So this is now one result with the web SDR captured photograph of one. I think it was NOAA 19. Another, this is a little bit more challenging, is to catch the voice transmission of Soyuz, because capturing transmission of Soyuz, this is not TLE that you can just pick it up on spacetrack.org. So what we do then to get it right at the moment where we need it, we log on to the TSUP live tracking, and then we try to make to reproduce this curve in order to estimate as good as possible when will be the next pass of our ground station. And once you're successful, you get the voice. So this is so there is also a little bit of orbital dynamics here. The students have to perform, and the good ones, they perform it well, and they can calculate it within half an hour, which is quite challenging, and then get ready to get the signals. Here is another very interesting Dmitry Pashkov. He has a very nice WebEx here, and you can also capture so use voice signals quite well with his WebSTR. So you can also do this at home, at your ease, and try it by yourself. Yeah, and of course, so receiving is one part of the job, but transmitting is another part of the job. And for that, the International Space Station with its digipeater is the perfect object. So there is also a lot of software that you can use. For example, this UISS. You set up your RPS message, and then you try to uplink. Sometimes this is also quite challenging, because most of the satellites have one receiving transponder and one transmitting transponder on different frequencies. And if you have a radio that is especially made for this, but for example, if you have an iPhone 910, which isn't really, for the setup, is not really meant to make this kind of transmission reception in half duplex. So you need to be a little bit more, let's say, creative. And at the end, you get your pin on the card, and which is also nice. So you know quasi immediately if it worked or not. And you can meet a lot of other amateur radio friends, which is also very nice. And then I thought I should not omit to mention PocketQube or Knife, which is a very nice satellite, has a very strong signal, although it's a CubeSat. And so this capturing this is it's not easy if you do it the first time. So you need a little bit of practice until you can get signals of PocketQube. But it's still in easy CubeSat. Okay. Some selected mission operations we performed. For example, we performed operations for Robusta. Robusta was a French satellite, actually, which downlinks at 435.3 megahertz in RPS, the typical RPRS mode, so AX25 at 1,200 bauds. And the purpose of that satellite was looking in time what are causes of degradation and what happens when satellites start to degrade. And yes, at the beginning, so we followed it up like 2 years. So at the beginning, we had really strong signals that we received with our antenna, with our Yagi antenna, and we were also able to, in principle, we were able to decode on the fly. But after a while, the satellite degraded, and so also the RPS signal became weaker, and it was not possible anymore to make it on the fly. So here we had to record it and then use the software of a well-known guy, Mike Kupprecht. He's quasi for 70% of the CubeSats. After 1 or 2 weeks, he has a new decoder for the satellite. So it's really an amazing guy. And with this software, we were then able to do it then to still make an offline decoding. Okay, so from our point of view, Robusta was a nice CubeSat. The signal was not that strong, and it degraded over time. So that was also interesting for my students here to make this follow up about the signal. What was not so nice was that the beacon actually was transmitted, I think, every 5 or 6 minutes. So even if you had a good pass, at max elevation of, let's say, 70 degrees, but if you were unlucky and it sent, let's say, at 12 degree elevation, the next time it would send, it was already too far away. You see the signal in the waterfall, but there was no way to decode it. So that was maybe something that was not that optimal. Yeah. And this is also important for satellite builders. Documentation is very important. The packet was very well documented because here in this case it was a packet that first has a protocol that's well implemented, so this is very important. And also inside the packet was very good documented, so it allowed the design of several nice decoders. Another satellite which is also, I think, interesting is VZLUSAT. It's a miniaturized X-ray telescope, has it in. It's also has this German feedback sensor for analyzing molecular oxygen. But they have an online ground station, and you can look into all the data from that online ground station, which is very nice. And it has a very strong signal. It's a very nice signal. Almost you can, at our ground station, if it's almost on the horizon, like 6-7 degrees, we can capture data until on the other side of the horizon. That's why we use it, although, and this is not so nice, there is no documentation about the packets, so you only can get your hexadecimal KISS files or whatever, but you have there's no way to understand what the satellite is telling you. So from our point of view, strong good quality signal, so it makes a lot of fun actually operating it and tracking it. Also the webpage is nice and informative and has an online ground station monitoring, but for us it would be nice to being able to decode the data. And also if you ask them if they could maybe give some information, so there is no one that actually has. Because it's not documented, so that's why we tried out to find, so how could you capture signal? It's GMSK at 4,800 baud, modulation in AX25 packet format. So if you use that, at least you can decode and get some nice hexadecimal numbers. Okay. At our university also we built a satellite that was Compass 2. And for us mission operators, Compass 2 was a really hard time because we trained a lot and our engineering model is working fine. We worked out all the procedures for commissioning and everything. And also, like Jaroslav said, we also did the RF setup in the world setup, and everything was very fine. But once launched, nothing. And this is, as point of view of a mission operator, this is something that always can happen. 50% of all CubeSats just don't work. And that's why we still keep an eye on it, and we are grateful for every amateur radio that would still try to capture our Compass 2. Then this was a very interesting time. Star C, the Japanese satellite. Actually, it's two satellites that were coupled together by this keeper. But this little bird had some problem with their receiver, which they thought that it was the antenna that didn't deploy. And so they had also the problem that their ground station was somewhat basic, let's say poor, and so they had really problems operating it. And so they joined us and asked us if we could help, or maybe first the beginning was just listening if we get signals. And then we realized, yes, the satellite is alive, so it became active again in a public matter. And then we got also the whole documentation in order to operate the satellite. So what we tried to do was then to first deploy the antenna and then deploy the theta. Took us a while, but at the end, and that's why this mission is so interesting, the satellite had a bug. Now we will call it a feature, because this bug helped us in order to operate the satellite. Since it didn't have RPRS, because the receiver was dead, but the transmitter was dead, but the receiver still worked. But the interesting thing, so if you send the command up and you get no information about the reception, but because it was built with a simple processor, so it had no multi-threading, and that's why when it was sending the beacon, and it would then capture the command, then the beacon would be interrupted, so at least to know, aha, the command has been sent. But wait, what is very important is you have to send the command always when the beacon has been sent, because otherwise you won't get the information about the reception. And that's why we were very lucky. That was also the purpose why we implemented our second teleport, because at the teleport A we were setting up we were uplinking the command. But the problem is when you uplink the command, although we have this JPOL filter, our transmitter is so strong that it will overwrite. So the signal in the band where the more signal is kept, and so you really can't be sure if it works or not. So with our second teleport, which was a little bit more far away, we were able to listen and then actually look, it has been sent. You see it a little bit here, but still you can see the Morse beacon. And then we could look, the beacon has been stopped and began the line from the beginning. And so we realized that at least the uplinking of the command was successful. Yeah. So from our point of view, the CV beacon was really from a good quality. So when it entered at 15 degrees, we kept the CV beacon very well. Then, because it's an ISS orbit, when it was at the nearest, it was super difficult to capture the signal or to decode the signal. So we used a lot of automated Morse decoders. They all failed. So we had to really write it down, and I never had the time to learn it, but there are some online tools. You just type the DDA dots and then you get your information. But we have students that really sit there and now can talk in Morse code. So that was very, very, very interesting from my point of view. And yeah, so this bug that the satellite had saved our day. And okay, now the most interesting thing, PocketQubes. So, and I think until now the best PocketQube ever. There's not so many, but still, you can say, from our point of view, $50 that was the best PocketQube ever, with its simple RFM22B, and it was well designed, not only from a more electrical point of view, but also the features it had. It has several modes for the transmission. So it had CV beacon, a slow CV beacon, telemetry beacon. It had also a very fast CV telemetry beacon. So at least if everything fails or the signal is so weak because you don't have a good path, if you can hear the beacon, you get some information. Also, because it varied the speed, you get also information in this. So the same beacon could be played in a faster way, and that was there was then encoded the information about the power health of the satellite, which I think is very simple and innovative way. It had RTTY, which is a well-implemented protocol, a way of modulation. And then it had also this challenging, weird modulation format of the chip itself, this RFM22B. It had everything you need, even if you don't have this chip or don't want to plug this chip inside your ground station setup, because this was actually needed if you want to understand this high resolution data. You had to take the chip and insert it, plug it onto your antennas. You could get some results. At the time, $50 that was in space. We didn't have the practice. We were trying to catch our friend, but we had the recordings, and so with the students we tried to take these all recordings and look if we would be able to decode. So here is the CV multiple, and yeah, we got at least we got the information about its call sign. This is FLDG, and for the RTTY we didn't have any, but on the well-documented, still existing web page, you have the wave files, and so we tried. Is it really possible to get the information? And yes, very easy. It's very easy to decode $50 at RTT. I didn't thought that it was possible to use RTTY from space and get signals decoded, but very flawlessly. So from our point of view, it's really a pity that it was way out of its time. So we didn't were ready, because it might have made a lot of fun tracking this satellite. It had strong signals, and I remember when we were looking for VREN, so we looked also in the bands of where $50 was. The signal was omnipresent. Interesting feature for the operator is you could even put information in the speed of your CV beacon. So this is a cool idea. What was very interesting, and what made it, in my point of view, a great satellite, it was its simple design. So they really focused only on one specific purpose, and they put a lot of work inside of the transceiver and receiver, and offered various transmission protocols. It is a very documented satellite. It's really often when you are looking for information. So this is really an important message to satellite satellite constructors. Document your stuff. If you want amateur operators to help you, document your stuff. That's very important. They also had news group, blog, web page, Dropbox. Every time you tell them a question, they answer directly. So it was a great team. It was a great satellite and a great team. Okay, VREN. For us, for me, it was a very hard time, but it was an interesting satellite that Paul made there. That's your satellite. I don't know if I should say something about VREN. Maybe better the people ask you, or maybe you know everything about VREN already. But it was quite a fun thing, because it had full plasma cluster, reaction with attitude determination, camera for nadir tracking, analog image transmission in SSTV, power supply for solar cells. So there was quite a lot of stuff in just one P, and there was also he provided also the decoder, and yeah, in the laboratory it worked well, but reception was quite difficult. So also we think we got the signals. So very weak signal here. As long as it concerns me, I never was able to decode any signal of RAM. But still, yeah, it's lived and it sends some signals, I think. And it has also been heard by others who said that they sure to having captured it. Interestingly, that was now I didn't know, but also the WebSDR from South Africa, they captured the signal. It's still in somewhere in their blog. Dimitri Pashkov, which is undisputably one of the very prominent amateur satellite radio operators, says he got the signal. And also one guy of England, Patrick Kirkland. So yeah, maybe that was a signal. Also, they didn't have any chance to decode the telemetry beacons. So for us, it was a really hard time, a really intensive moment, being at the ground station, to try to capture it without any. But as it was also something very personal. Then you try to get your word. You see the signal, and you're always putting yourself in question. So this is something that will happen to you when you operate your satellite, and when there are problems. You still need to try to get on it and make your work, and not too much to personalize it, because this is something that really will work on your soul. That's very important. Yeah. So from our point of view, it was poor signal. Was it the transmitter that was weak? My predecessor explained what might have happened. That it was a really tiny room and a lot of electronics. Yeah, maybe this is really difficult to put all this in one satellite. I think also nowadays, I think that command updating by Morse encoding is not that optimal. When I realized decoding, especially when we operated Star C, decoding Morse signals for an automated system is, I didn't know, I didn't think that, but it's still very challenging. And so if you want to decode Morse signals, you need software with some intelligence in there. And I think in such a small room, there would not be enough room for the moment to implement this. So I think Morse encoding for uplinking is not a good idea. The proprietary modulation scheme was a really nice idea, but the problem is, because of that, you only could decode the signal if you use this decoding software. And maybe we would have more information about our satellite if we would have used Morse beacon. Simple Morse beacon, you listen to, you don't need any technical apparatuses, just listening and write down. So this is, I think, for PocketQube missions, you really should use CV beacon, not only for the beacon, but also as a telemetry beacon, where you get at least a little bit of information about what your satellite is doing. And of course, it was and I think like 60% no, 90% as far as I am concerned. At that time, I had a big lack in experience about receiving signals and understanding what I'm doing. So this is something you have to consider. Not only build a satellite, you have to experience in the reception, and also think in the design of your satellite. Is this design, how I did it, something that is practically useful? If you have a cool satellite with a lot of science data that you want to produce, and the reception and the transmission is too complicated and too awkward, you have a big risk of getting nothing from it. That would be very sad. And but still, it was the first 1P PocketQube, and it was great work from Paul. So for me, it was the entrance in a new field. I come from somewhere completely different, and because of Paul, he made me he get me the virus of space, and that's why I'm really thankful about this. Okay, so that was. Yeah.
Great presentation, great work on operations and stuff like that. But we also need automation, right, and scheduling and those kind of things. So
no, we don't use automation and scheduling. And this is a decision. This is not. This is a decision because I want that the students are aware about it. They have to. So they make the schedule, and we have a storyboard. How do you do this? And we operate every time with someone on front of the consoles. Yeah. This is because otherwise we just would be a user of setnox, but it's a really interesting thing, and I think it's really important to have setnox. But our purpose is to get the students hands-on. So that's why we don't use any scheduling automation.
As an operator, what would you suggest to us builders is a minimum beacon time or an average beacon time?
Yeah, I would say you have to consider that when you have a grade pass, and you have not that many grade passes, I heard about 15 minutes. It's not 15 minutes. It's really not 15 minutes because that depends on where you are located. If you are in Austria, somewhere at down, and you have mountains everywhere, maybe you have 6 minutes, maybe. And this is then the ideal case. But most of the cases, you have poor elevations, and then you have less time. So if you have beacon transmission every 8 minutes, you'll not be a happy camper. No? So as Professor Malpras from the Kentucky University said, and he is right, the optimal way would be 30 seconds. I know it's challenging. The power consumption is amazing. No? But let's say 30 seconds for some satellites is challenging because of the power. But I would say everything more than 1 minute is bad. Yeah.
Reduce the consumption of plastic. So for the ones that don't need it, because tomorrow they are not coming, please, can you please put the pages on the table. For the rest, enjoy the evening, and I'll see you tomorrow.